I mean, it's scheduled for Thursday, but I have no problem with you taking it early.
Yeah, I can.
I knew you couldn't. So. Okay, just, I'll be around. I mean, if you could let me know when you want to do it,
Yeah.
that would be convenient. But I'm here from 10 to late on Monday. Yeah. So, but I'll be here from 10, so. I've already prepped all the exams, so. So review for exam 2. So exam 2, you take it next week. All the exams are prepped. So you can just send me an email when you want to take it next week and we can work it out. So let's go through review. So some quick review about wavelength, frequency, and energy. Oh, an exam is open book, open note.
Yeah.
Much like the last one. Speed of light is equal to wavelength times frequency. Energy is equal to Planck's constant times frequency, or Planck's constant times speed of light divided by wavelength. So here are some examples with 500 nanometer light. I'm not going to go through the calculations. You're just multiplying or dividing by the frequency. Remember that by the wavelength. And multiplying by the frequency. So remember the units. So absorption spectroscopy. When you absorb light of a specific wavelength, you're going from one state up to another. The difference in energy levels is equal to the energy of the light. So H Planck's constant times the frequency. This transition for UV visible will be a change in electronic levels. It can be electronic levels, vibrations, rotations, translations, etc. UV visible would be electronic levels primarily. The power of beam that reaches a given area per second is P. Intensity is the power per unit solid angle. Beer's law says the absorbance of light absorbed by a sample is dependent on the path length, the concentration of the sample, and a proportionality constant, the molar absorbability. And the important here is that if you have one measurement with a known concentration and another measurement with an unknown concentration, you can find the unknown concentration with these formulas. Much like you did on the first test. So if a solution that was 1.5 times 10 to the minus 3 molar in X had an absorbance of 0.45 when measured in a 1 centimeter cell, an unknown concentration of X generates an absorbance of 0.125. When a 1 centimeter cell is used, what's the unknown concentration? So do this quickly and I'll do it with the pen here. You know, absorbance 1 over absorbance 2 equals concentration 1 over concentration 2. So concentration 2 equals concentration 1 times absorbance 2 over absorbance 1, which will be, the reference was 1.5 times 10 to the minus 3 molar. Let me fix those nasty bits. And then you multiply by the new measurement, 0.125 over the old measurement, 0.450. And fix this. And that will give a final absorbance. Oh, where did I put a calculator in there? One final concentration of 1.5 times 10 to the minus 3 times 0.125 divided by 0.45. It's not going to fit there. .17 times 10 to the minus 4 molar. Basically divides by a factor of a little more than 3. For optics, so materials that you use for that are transparent, so cells, windows, lenses, and prisms. These are different materials you can use in different ranges. Lithium fluoride, silica quartz, quartz gas, silicate glass, NaCl, potassium bromide, and so on. Here are some absorption characteristics of some common chromophores. All kinds do the frequencies they absorb at. Here are some other examples of some common chromophores. Solvent can also absorb in UV visible, so the appropriate solvent to choose. These are the lower wavelength limit you can detect. So below this limit, you can't really detect stuff. So water, it's 180, ethanol is 220, hexane is 200, and so on. So you need to, what a good solvent would be. Then mass spectrometry. For mass spectrometry, you're measuring the atomic or molecular weight of an ion from the separation based on its mass to charge ratio. This is based on the elemental composition of matter, the structures of inorganic or genetic, biological, this is what you can measure. It has very good detection limits. The instruments are expensive and can drift. They have remarkably simple spectra. And it's easy to measure, it's able to measure isotopic ratios. So this is the table of the relative abundance of natural isotopes. Some useful, relevant things for this is if we look at so some relevant things. Chlorine is 75-25 between 34 and 37, 34 and 36. Sorry, no, 35 and 37. Sorry. And then another one that's relevant. Bromine is the other one that I wanted to mention. Bromine is basically evenly split between 79 and 81. Those are some relevant things. So you'll see that sort of splitting in the spectra. There's the nitrogen rule. So based on an anomaly of the relationship between atomic weights, the valences of common elements, an organic molecule containing the elements of carbon, hydrogen, oxygen, sulfur, phosphorus, or halogen has an odd nominal mass if it has an odd number of hydrogen atoms, and an even nominal mass if it has an even number of nitrogen atoms. So for this ion sources, the formation of gaseous aniline ion, used to gaseous aniline ions, they come in two types, hard and soft. hard sources shatter into many pieces and are good for figuring out structure. Soft don't and are good for better for figuring out molecular weight. So electron impact, for example, is the two most common are electron impact and chemical ionization. Electron impact is hard, chemical ionization is soft. So electron impact is good for identification. Chemical ionization is good for getting the mass. So this is exposure to an electron spin or reagent gaseous ions. And there's speed-all ionization, which is soft, field desorption. And there are gas phase and desorption methods. Gas phase methods act on a gas. Desorption methods act on like a solid material and cause it to spray off. So then there's field desorption, electrospray ionization, matrix assisted desorption ionization. Those are all soft. Plasma desorption is hard. Fast atom bombardment is soft. Secondary ion mass spectroscopy is soft. And thermospray ionization is soft. Hard sources have sufficient energy, so the analyte is in a highly excited energy state. This produces fragment ions with mass to charge ratio less than the molecular ion. This gives kinds of functional groups and structural information. So this is an example of hard ionization. You can see you get lots of things with various clusters of peaks. And so these are some examples, some more examples of hard ionization. And here you can in fact not see the precursor. Soft sources primarily give you the whole ion, maybe minus OH or -1. They cause little fragmentation. They give you an accurate mass. But are hard to use. They're not quite as good for fingerprinting. So here's the same substance with a hard source and with a soft source. You can see the soft source has a big peak at M+1 and M+, so but the hard source has no peak at the mass and the scatter. With an electron impact source, sample is heated to produce a molecular vapor. You bombard it with a beam of electrons, and these form positive ions, which is not very, which is then fed into the mass band. It's a hard source, and the relaxation results in extensive fragmentation, and you could have some rearrangement and such. So here, for example, you see the molecular ion peak is very small, while the biggest peak is one of the fragments. The base peak is defined to be the most intense peak, and it's usually a daughter ion or a fragment ion. You do get peaks at molecular weight greater than the molecular ion from stuff recombining, or M+1 peak, which is a collision product. It's got good sensitivity. The fragmentation makes unambiguous identification of analytes. You need to volatilize the sample, and you lose the molecular ion peak, so it can be hard to find the molecular weight. Chemical ionization, basically the same setup as electron impact, but you add a reactive gas, a gas which gets hit by the electrons and then reacts with the analyte to form ions. But you can easily design something to do both. It's a soft source. The most common reagent is methane. And you tend to generate M-OH, maybe M-1 or M+. You often get M+1, M-OH, or M+ C2H5, which is N plus 29. Those are some common things that are formed. Plus one and minus one are pretty common. That's, adding a hydrogen or adding a proton or removing a proton. A hydride transfer. But you don't get a lot of. And the matrix assisted laser desorption is good for large polymers, pulse lasers to blow it off of to basically vaporize a matrix and carry them, animal it along as it flies out. There's almost no fragmentation. It has low background noise at high molecular weight. And so you need to be careful. It works for certain analytes, and it's fairly simple. Electrospray ionization, where you run it through a capillary and spray it out, but the capillary is charged, and then the solvent evaporates off, leaving behind the charge that was put onto the droplets, the aerosol. The needle's at several kilovolts of potential, and you aerosolize it, forming tiny droplets. Fast atom bombardment, you bombard it with fast atoms, which ionizes and then blows the material off of a surface. This reduces the very rapid sample heating by bombarding it with fast atoms, reduces sample fragmentation. Now here's an example problem with chlorine. We're identifying the ions responsible for the peaks in the mass spectrum for 1,1,2 tetrachloroethane. So here you can see we have multiple peaks spaced 2 apart. I mean, I've done the best thing for whatever. And so you can see that this is something that has isotopes that are spaced 2 apart. And there's enough to get at least 2. So there's at least, if you're identifying the particular ion responsible, well, each of these has 3, so there needs to be at least 2 chlorine atoms there. It's probably 3, and then you can look at the molecular weight. So the lowest chlorine could be is 35. So we have 117 here. You have at least 2 chlorines, so that's minus 35 times 2. So if you're looking at this bottom one, this is, so we have at least 2 chlorines. So that's 35 times 2. That leaves you 47. Looking at the structure, this bit here could easily be a unit, and that's 3 chlorines on a carbon. So 35 times 3 plus 30 plus 12 gives you 117. So this is equal to 35 times 3. That's, Cl3 plus 12. That's carbon. And then you get the additional peaks because, a quarter of those chlorines are a heavier one, and then another. So sometimes 1 is heavy, sometimes 2 are heavy. Unlikely 3 are heavy. And then over here we have at 131, the step from 117 to 131, that difference is 14, which is a carbon and 2 hydrogens, which is this. So this ends up being, because this is plus 14, that's plus carbon plus 2H. So that's Cl3, C2, H2. So the first one is this unit, and the second one is that unit. I'll make sure to save this version of it and put them up. Because I am right now just writing it, but I'll make sure to do that after the end of this. And it was already there. So let me actually undo that and include what was already there. So those are already there. 12 plus 3 times 35, that's 117. 12 plus 12 times 1 plus 1 times 2 plus 3 times 35, that's 130. And I think I may have possibly done something slightly wrong. I need to check what I need to do on somewhere. So here we have a double focusing analyzer. This is one of the ways you can measure mass to charge ratio. This is one of the ways. It goes through electrostatic analyzer and magnetic and focuses out for different mass to charge ratios. And here's a quadrupole analyzer that's more compact, less expensive, and rugged and rapidly scans. It uses alternating electric fields on these poles to basically create filters. And the thing is that this has a higher resolution, but this has a good enough resolution to get whole numbers, which is often all you need, all you want. And it still has a decent resolution. It's just a lot of the time for mass spectrometry, all you really want is whole number. You're interested in the whole number values. A time of flight mass analyzer is sort of the simplest one. It's just a tube. Sample is generated by some method during some sort of pulse, and then it travels along the tube until it's detected. And it's accelerated here. The lighter things travel faster than the heavier things, so they're detected first. Then we have chromatography. Chromatography is the separation technique based on different reactions of compounds. There's 2 phases. There's a mobile phase and a stationary phase. The mobile phase is whatever flows through the supporting medium. The stationary phase is some layer or coating on the supporting medium that interacts with the analyte. And the supporting medium is just a solid surface on which the stationary phase is bound or coated. So you start, and if you have 2 substances that interact with the stationary phase different amounts, you start with them mixed together, and as they go through, the one that interacts less travels through faster than the one that interacts more. And so first B emerges, then A emerges, because B interacts less than A. Chromatography is primarily separated into gas chromatography that uses gas as its mobile phase, and liquid chromatography that uses liquid as its mobile phase. For gas chromatography, there's gas solid, gas liquid, bonded phase gas chromatography based on the type of stationary phase, whether it's solid, liquid, or some chemically derivatized support. We used bonded phase. And for liquid chromatography, based on what your the interaction with the stationary phase, you have adsorption chromatography, partition chromatography, ion exchange chromatography, size exclusion chromatography, and affinity chromatography. You can also classify them based on how the support material is set up. You can have a packed tube, a porous layer open tube, or a wall-coated open tube. So a wall-coated open tube is the most common for gas chromatography. Packed tubes are fairly common for liquid chromatography. You can also have a bed like this, where it's a flat bed. So gas chromatography, chromatographic technique where the mobile phase is a gas. It's popular. It can be applied to any compound that's naturally volatile, or it can be converted into a volatile derivative. So it's good for small organic and inorganic solids. You have a gas source, an injector, a column, and a detector. And it separates solutes based on the different interactions with the mobile and stationary phase. And its retention is determined mostly by vapor pressure and volatility, and controlled by its interaction with the stationary phase. The mobile phase basically does not interact with the substance. So it's all about the interaction with the stationary phase, and the mobile phase is just a neutral gas carrying things, which is why it's often a gas that really doesn't react with anything like, And then you can covalently attach the stationary bonded phase gas chromatography is where you covalently attach the stationary phase to the solid support material. There's many different things that can be used. This is the advantage of it's much more stable than liquid phases and can be placed on support with thinner and more uniform thickness than liquid phases. So open tubular stationary phases, you have bound polymer like phases. And you can use either polar or non-polar for different things, interact differently with different substances. So your choice there. We did all our stuff with what is basically this one, SLB5MS, the equivalent of that. It has a slightly different name because it's the Thermo Fisher brand of that, but it's the same thing. Now, a common problem with all chromatographic techniques is that in any one sample, you could have lots of different solutes present, and they're each retained by different degrees. And basically, different conditions will be better for different solvents. And so you want to get this K prime value between about 2 to 10, but it's really difficult to find one condition that elutes all solutes in this K prime range. Where, for example, if you optimize for 1 and 2 here, 3 and 4 is okay, but 5 and 6 have spread out too much and are hard to see. Well, here, if you optimize for 5 and 6, 1 and 2 and 3 and 4 are glommed together. And here for 3 and 4, 1 and 2 are glommed together. 5 and 6 are starting to get spread out and hard to see. So the solution is you do a gradient dilution. You change the column conditions over time. So you start in this state. When you start in this state, then you sort of move to this state, and then you finally move to this state. And what you do to do this in liquid chromatography is you change your mobile phase, you change what mixture you're using. In gas chromatography, you change the temperature. So gas chromatography, unlike liquid chromatography, uses temperature programming. You can do an isothermal separation where the temperature remains constant, or you can do a temperature gradient or a programmed process. This requires a computer-controlled oven, but honestly, a computer-controlled oven is not that complicated. So temperature programming allows you to change the temperature of the column with time to simulate the gradient dilution. in GC since the solutes retention is related to its volatility. So here's an example of this is isothermal, where everything's at 120, and here is a ramp at 5 degrees per minute. And you can see how all these are merged together in this one, while on this one, all the peaks are nice and separate. And this is why you use peak area instead of peak height, because you can see here this peak height is a lot shorter. But here the peak area is about the same between them. So because the conditions are changing, peak area is much better than peak height for that. And also just generally peak area represents the amount of stuff better than peak height does. So here, if you have a 0.5 microliter reference sample of 5% ethanol spiked with a 1% N propanol internal standard, it has a peak for ethanol with an area of 5520 picoamps by picoamp minutes, and a peak for propanol of 1150 picoamp minutes, and then a second 0.5 microliter with an unknown ethanol also spiked with the same amount of N propanol, has a peak for ethanol of 3500 peak amps minutes, and a peak for N propanol of 1150 peak amps per minute. Well, we know the 1150, we know the N propanol corresponds to the same, works as a reference standard. So it tells you that you're getting the right amount of sample. And because, so basically what you can do for this is, your concentration 1 over concentration 2 is going to be peak of ethanol 1 over peak of ethanol 2. It's like it's just a standard ratio thing. And then there's a correction you put in for the propanol peaks, which would be actually it would be just to make sure that you're having the right thing, it would be a peak of propanol 2 over peak of propanol 1. Because if the propanol, so like, if you're seeing a bigger propanol peak and you know that corresponds to the same concentration, you need to lower the size of the appropriate ethanol peak. So basically you're doing ethanol over propanol over ethanol over propanol. But in this case, the propanols are the same. And then this just comes out, the way you'd end up doing this is that it would be concentration 2 is concentration 1 times peak of ethanol 2 over peak of ethanol 1 times peak of propanol, peak of the standard. I should make these standard 1 over. Okay, but no, let me erase some of this. This is all very sloppy. Sorry. I'll just make these. I'll leave these as propanol. I hate this particular bug that causes weird jumping. Peak of propanol. Yeah. Oh, these should be area, not peak. That's a better way to write this, and it'll be less confusing. Sorry. Why does this, I hate this particular bug. It's a, so concentration, area. You know what, I'll just leave that. Area propanol 1, area propanol 2. So that's going to be 5% times 3,500 over 5,520, and then times 1150 over 1150. So 5 times 3,500 divided by 5,520. This is 3.17%. So that's just an example. And these are some common GC detectors. You have a thermal conductivity detector, flame ionization detector, nitrogen phosphorus detector, electron capture detector, and mass spectrometer. Thermal conductivity detects everything, but it's not very sensitive. FID detects hydrocarbons. It's quite linear, easy. It's sensitive to both things, but it's destructive. NPD and ECD is similar to FID, but focused on nitrogen sulfur compounds or halogenated compounds. Mass spec detects almost everything, but it's expensive and complicated. So a thermal conductivity detector has 2 paths, where one is a reference stream and one is the output of the GC. And when the thermal conductivity of these is different, that changes the voltage here, and that can be detected. So it detects changes in thermal conductivity. This is why you use hydrogen or helium for it, because their thermal conductivity is very unlike other gases. So when that uses a Wheatstone bridge, hydrogen and helium are the chemical carrier gases. And the presence of the analyte increases the ability to conduct heat, so filament increases in temperature, and the resistance changes. So mobile phase has to have very different thermal conductivity than solutes. It's truly universal. It's non-destructive, but it's not very sensitive. And it can be sensitive to changes in flow rates and other impurities. Flame ionization is the most common gas chromatograph detector. It measures the presence of almost any organic and many inorganic compounds. It burns the substance in hydrogen, which creates a hydrogen flame, which creates ions, which are detected by an electrode. It's quite sensitive. It's what we used. It doesn't respond to some common inorganic compounds, which is kind of nice because it deals with like air contamination and things. Mobile phase impurities are not detected. Carrier gases are not detected. And the limit of detection is 1,000 times better than a thermal conductivity detector. The big disadvantage is it's destructive. Then there's high performance liquid chromatography that uses the liquid chromatography with small uniform rigid support material, has good system efficiencies at small plate heights. You have narrow peaks, low limits of detection, short separation times. And the columns can tolerate high operating pressures and faster flow rates. So this uses some high operating pressures needed for the mobile phase. Delivery requires special pumps and other system components. and the sample is applied using a closed system, i.e. an injection valve. And the injection uses some sort of flow-through detector. So it has fast analysis time, it's easily automated, it has good limits of detection, it's the preferred choice for analytical applications, popular for purification work. The disadvantages, it's expensive, it doesn't have very high sample capacities compared to other liquid chromatography methods. Then we have NMR, the theory of NMR. Nuclear spin, think like electric spin. The nucleus rotates around its axis. Nuclei with spin have angular momentum. This is quantized with a spin to quantum number I. You get 2I plus 1 states. I minus 1, I minus 2, down to minus I. These have identical energies in the absence of an external magnetic field. In a magnetic field, they will split into different energies. NMR active nuclear spin tend to be things with I of 1/2, like hydrogen 1, carbon 13, nitrogen 15, fluorine 19, or phosphorus 31. They have an odd atomic mass. I is plus 1/2 or minus 1/2. NMR inactive nuclear spins are one with 0. These are ones that have even atomic mass and number, like carbon 12 or oxygen 16. And then there are ones with quadruple nuclear spin, where I is greater than 1/2. These tend to have I of whole number, even atomic mass and odd number. They tend to have I of 1, plus 1, 0, and minus 1 are the relevant ones. So nitrogen 14, deuterium, boron 10. So if the number of protons is even and the number of neutrons is even, I is 0, there's no overall spin. If the number of protons plus neutrons is even, then I is 1/2 or a multiple of 1/2, like 3/2, 5/2, and so on. The number of protons is odd and the number of neutrons is odd, then I will be 1 or an integer multiple of 1, like 2, 3, or so on. But 1/2, 0, 1, and 1/2 are the most common ones. So magnetic moments are oriented in one of two directions in a magnetic field. This is the Zeeman effect. In a magnetic field, these levels will split. It was first observed with electrons, which have spin 1/2. You see the electrical energy line splitting in a magnetic field. And it's actually quite useful. You can use it to measure magnetic fields of distant objects. The difference in energy between the two states is given by the external magnetic field times Planck's constant times the gyromagnetic ratio, which is a unique value per nucleus, divided by 2π. The frequency of absorption, so the observed NMR frequency is going to be the gyromagnetic ratio times the magnetic field divided by 2π. And then the distribution, the splitting between the levels is given by Boltzmann's equation. So if you put a bare proton in a magnetic field of 3 Tesla, the energy difference between nuclear spin phases would be h bar gamma b. So h bar is just h divided by 2π. It's 1.05 times 10 to the minus 34 joule seconds times gamma for a proton, which is 2.675 times 10 to the 8th inverse second inverse Teslas times 3 Tesla gives you 8.43 times 10 to the 26 joules. The wavelength of that photon, well, you can find the frequency, is 127 megahertz by basically dividing the energy by h bar. And the wavelength is h bar times c over the energy, and that's 2.36 meters, which is a radio wave. And so the first NMR was done by doing a sweep. There would be an absorption peak at the particular sweep. You could sweep magnetic field, or you could sweep radio frequency. You can also generate these same equations classically by thinking about a spinning particle processing in an applied magnetic field. You get the same result for the frequency. Gyromagnetic ratio times b divided by 2π. So here for some common data, the magnetic moment, the magnetogyrotic ratio, of 10 to the 7 radian Tesla inverse seconds, for various nuclei. Pretty sure I'm giving that on the table on the test. And the relative sensitivity of proton, of hydrogen, carbon 13, nitrogen 15, and other nuclei depend on the gyromagnetic ratio and the natural abundance of the isotope. The gyromagnetic ratio can't be changed. The sensitivity is proportional to the gyromagnetic ratio cubed. So protons are 64 times as sensitive as carbon 13 and 1,000 times as sensitive as nitrogen 15. But there's also abundance. Hydrogen has an abundance of about 1, while carbon 13 is only 1.1%, and nitrogen 13 is 0.37. So the sensitivity difference increases to 64,000, 6,400, and 2.7 times 10 to the 5. So you got to take more measurements for carbon 13. We got away with as few as we did because we had lots of sample. Most solvents used in NMR are organic. So the solvent is present in overwhelming concentration relative to the sample. The sample signal will get wiped out. The solution is a deuterated solvent, where all the protons are replaced with deuterium. Deuterium has a Lamar frequency outside of the range of regular hydrogen, and it can be a structural probe for other things that undergo proton exchange reactions like OH and such. And a strong deuterium signal provides a convenient lock signal. So, deuterated solvent, useful. We did that with the heavy water. That's our deuterated solvent. Chemical shift is frequency minus base frequency over the over the base frequency. It's measured in parts per million. Low. So this is D shielding, and this is high shielding. This is local field opposes B naught. This is D shielding. This is ethanol. If you wanted to see what it should look like, we have the CH1, CH2, and the OH. Here are some chemical shifts for protons, roughly. Here's a table with various chemical shift ranges. These tables are a little better, maybe a little more helpful than and then the splitting pattern tells you what atoms are nearby. So equivalent nuclei don't interact. But you get a coupling tied to the number of peaks you see is 2ni plus 1 lines, where I is the nuclear spin number, which is probably going to be a half. For everything we did, it was a half. And n is the number of neighboring spins. So generally, you get a number of peaks equal to the number of neighboring spins plus 1. So for example, in ethanol, that CH3 group, the neighboring spins is the 2 hydrogens in the CH2 next to it. So it splits into 3 peaks. The CH2 had 3 neighboring spins, so it split into 4. And the spacing is independent of applied field strength, but yeah. So this is the proton NMR spectrum for a compound of empirical formula C4H8O. We want to identify the compound. This is the reference peak. We have a strong sigma peak, So one singlet peak here, quad peak here, and a triple peak here. The strong singlet at 2.25 ppm corresponds to a methyl next to a carbonyl. The absence of a peak at 9.7 ppm highlights the aldehyde group and suggests a ketone. The quartet at 2.5 ppm suggests a methylene next to a carbonyl coupled to a methyl. And the triplet at 1.2 ppm suggests a methyl group coupled to a methylene group. So this is the structure. So the quartet is this CH2, the triplet is this CH3, the singlet is this CH3. Lastly, we have MRI. The fundamental concept of MRI is that by applying a gradient magnetic field, you can encode positional data into the frequency, and by applying gradient magnetic fields, you can employ positional data into the frequency and phase of NMR peaks. So you're looking for the same thing everywhere. You're not differentiating so much by chemical shift, but by applying a gradient, the frequency will vary depending on your position in the physical object. And by applying additional gradients, more complex pulse sequences and more than one dimension of positional data can be encoded. So the general process is you excite a slice, and then you can get 2 dimensions of that slice by applying appropriate gradients during the pulse sequence. So you first have a pulse. You first have a gradient and a pulse period with Y, which sets up the phase. And then you let it settle down with a gradient in X, which sets up the frequency. So the phase encodes your Y position, the frequency encodes your X position. And then the strength of the peak encodes how much hydrogen there is there. So it can correspond to density of flesh. So a shaped pulse and magnetic gradient along the z-axis, you could only flip the spins in one slice, and the flip spins get excited by a pulse and allowed to process in the field gradient along the y-axis to encode the y position as a phase shift, and then the gradient along the y-axis is turned off, and gradient along the x-axis is activated, and the x position is encoded in the precession frequency. And more complicated patterns can be used to better observe different organic molecules, make those stand out. So if you want to look at fat, or you want to look at muscle, or whatever you want to look at. And MRI pulse patterns are like black magic that I do not understand. And then lastly, we have Raman spectroscopy, which is the complement to IR spectroscopy, where radiation at a certain frequency is scattered by the molecule with shifts in the wavelength of the incident beam. And the observed frequency shifts are related to vibrational changes in the molecule. And they will create peaks in the same sort of places where you might see IR peaks. So Raman scattering spectrum resembles IR absorption spectrum, but the Raman and IR mechanisms differ. They both look at vibrational modes, so they're both sampling from the same set of frequencies, but IR looks at a change in dipole, while Raman looks at a change in polarizability. And this leads, and Raman and IR involves the excitation of the molecule to an excited vibrational state, while Raman involves the momentary distortion of the electrons distributed around the bond. And the most important is that asymmetric vibrations are active in IR, while symmetric vibrations are active in Raman. So they basically they detect the 2 different halves. So where an IR peak is weak, a Raman peak will be strong, and vice versa. So light is scattered at the sample at various angles by momentary absorption to a virtual state and re-emission. It can either be absorbed and then return back to the same level. So it could go from the ground state down back to the ground state. It could go from an excited state back down to the same excited state it started at, but it can also go from the ground state down to the excited state, that's Stokes scattering, or it can go from the excited state down to the ground state, that's anti-Stokes. So these are Rayleigh scattering, where it goes back to where it came from. Raman scattering is where it goes back to somewhere else. Rayleigh scattering is a lot more common and bigger than Raman scattering. So most scattered emissions occur at the same energy, while some return to a different state. Those are the Raman scattering. These are elastic. These are inelastic because there is a change in energy. And Stokes is more common than anti-Stokes. So Rayleigh peak is biggest, then Stokes, then anti-Stokes. The energy, the most common, you're just going to see the energy plus or minus delta E is the energy of the first vibration level of the ground state. The Raman frequency shift from the IR absorption peak frequency end up identical. Stokes is plus delta E. Sorry, Stokes is minus delta E. Anti-Stokes is plus delta E in frequency. But because for anti-Stokes you have to start it at the excited state, it's less common. So the general process is Rayleigh scattering is biggest peak, then Stokes, then anti-Stokes. And the intensity of the Raman lines are something like 0.001% of the intensity of the source. So you have to block out the source or ignore it. And active Raman vibrations are, you need to change the polarizability of the molecule during vibration. So for example, in CO2, this symmetric stretch is IR active, but Raman active. While this asymmetric stretch is IR active, but Raman inactive. So IR and Raman are complementary. There can be cases where both IR and Raman are active, like in sulfur dioxide, which is a nonlinear molecule. But in general, IR tends to emphasize polar functional groups. Raman emphasizes aromatic and carbon backbone. And it doesn't see many common polar solvents, which can be helpful because you can use aqueous samples, which is an advantage over IR. And the Raman frequency range is around 4,000 to minus 50 inverse centimeters. And this is sort of the instrument design. You send it into the sample, it gets scattered and detected. And generally you use a laser to get the required intensity of light for reasonable signal to noise, because the Raman is so much smaller than the light source. It doesn't have to be in the IR region since you're looking at a change around a central peak. So you use visible sources because of high intensity, and you can use glass quartz sample cells and optics and UV visible type detectors. It's good for characteristic regions for different groups. This is an IR. Raman correlation charts are good. It's good for aqueous-based samples. It's used for a variety of samples. It's not that oftenly used for quantitative. It has interference from fluorescence. It's more expensive. The signal is weak. It's better for qualitative than quantitative. But yeah, here we can see for a stretch like this, you get a polarization change. Symmetric vibrations lead to relatively strong Raman signals and no IR. Asymmetric vibrations lead to weaker Raman signals, often quite strong in IR. Bending modes lead to much weaker Raman signals and are often quite strong in IR. The molecule can have both IR and Raman signals at the same frequency. So if the Raman signal is strong, the corresponding IR peak will be weak and vice versa. If you have an asymmetric molecule, it's likely to have both, but one mode will be strong, the other will be weak. So here's CO2. This will be active in Raman and inactive in IR. This will be active in IR and inactive in Raman. And the bending modes are also not Raman active, but are active in IR. Here's a Raman spectrometer. You can also have you can also have the scattering be directly back, which I think is what ours does. And the source, they use laser sources like argon ion, frequency diode laser, things like these. And here's a side-by-side comparison. I'm not gonna go through this right now. We went over it when we did it, but you can read it on your own. And that is the end of the review. Any questions? I will make sure to save this and replace the review online right now.